Assalamualaikum and hi, this is the introduction chapter for video part 2 of heat transfer BMCG4743. Okay, heat transfer. So what we are interested in the heat transfer is, and what we are doing in the heat transfer is we predict the energy transfer from the heat, which is coming from the temperature difference of high temperature and the temperature, the heat energy will goes from high temperature to the low temperature. So we have temperature difference here, so T1 should be larger than T2 for this case to happen. And we are interested in the how heat energy being transferred. So basically we have three modes of heat transfer, and we are also interested in the rate of heat energy transfer. So let's see one example here. So we have hot water which is at the 100 degrees Celsius and a steel bar at 25 degrees Celsius. Initially, the condition is something like this. So the water is in the 100 degrees Celsius and the steel bar is at 25 degrees Celsius. And after 1 hour, which is the current state, the water temperature start to decrease because the heat energy is being transferred to the steel bar, which has lower temperature. And then after 2 hours, okay, as stated in the slide, 2 hours, okay, 2 hours here, and this is the 1 hour. Okay, after 2 hours period, both condition, water and the steel bar has same temperature. So in this condition, it's being called as the equilibrium state. So in this case, we are interested in the rate of heat. Current temperature, rate of heat is the amount of heat being transferred per unit time, and time required. Okay, so the overall time required to transfer heat from the water to the steel bar. So there are the three things that you are interested in the heat transfer analysis: okay, rate of heat transfer, current temperature or the temperature, and also time required to achieve equilibrium state or the heat to be transferred from one body to another. So we have two cases in the analysis of heat transfer. The first case is the steady state heat transfer. Okay, heat flow continuously at a uniform rate, okay, which is given by this example. Okay, let's say we have a hot body and transfer a 5 kilojoules per second of heat to the cold place at the initial state is 1 second, and then after 5 seconds the heat that been transferred from the hot body to the cold body still 5 kilojoule per second, as you can see here. So 5 kilojoule per second at t equivalent to 1 second, and then after some time, which is here stated as 5 seconds, the heat transfer rate still same. So this kind of thing is being called as the steady state heat transfer. So Q here is the heat transfer, and over time, okay, versus time, so the heat is in the constant value. So this kind of thing is being called as the steady state heat transfer. And then we have another case 2, which being called as transient heat transfer. Okay, the rate of heat flow changes with time. Okay, for example, okay, we have a hot body, transfer heat of 5 kilojoule per second at t equal to 1 second to the cold body, and then after a certain period of time, for this case 5 seconds, the heat transfer rate increase to 10 kilojoule per second. Okay, so this kind of condition is being called as transient or unsteady state of heat transfer. So if we plot the Q, which is the heat flux or heat transfer rate versus time, so the value is increased with time. So this kind of thing is being called as the transient heat transfer, or it's also being called as unsteady state heat transfer. The conduction heat transfer, which is the first mode of heat transfer, it is a heat transfer from the contact or solid body, between solid body, or within the solid body. Okay, from the temperature difference within the solid body. So the conduction heat transfer follow the Fourier law, which stated as follow: the rate of heat flow through a homogeneous solid is directly proportional to the area A at the right angle to the direction of flow and to the temperature gradient dt over dx along the flow direction. Okay, so if we take a small portion here of this prime pan, and we redraw it to be something like this. Okay, we can say that this bottom part is T1, which has higher temperature, and T2 has lower temperature. Why I said T1 has high temperature? Because of the direction of heat here, Q, from T1 to T2. Okay, so we take a portion of this and we redraw it to be something like this, and we take another portion here, this green area here. Okay, and we redraw it to be something like this in the three-dimensional. So dx here is dx here, which is the at a short period distance. Okay, T here is the temperature, and T plus dt is the change of temperature from the front surface to the back of this surface. So the surface area is here, the front side here, which is the cross-sectional area, or perpendicular, proportional, or perpendicular direction with the direction of the heat flow. So we can use the Fourier law of conduction. Q is directly proportional to surface area, okay, and also proportional to the dt over dx. Okay, if we plot this value, or if we plot the heat versus the A and also dt dx for a certain material, we'll get the gradient of the graph to be something like this. K here is the gradient of the graph. Okay, so from this K, dt is the temperature difference and dx is the distance, or the distance of x. Okay, so we can rearrange or rewrite the equation to be something like this: minus Ka A, okay, T2 minus T1 over x. X here is these things, and A here is the surface area, overall surface area of this condition. And K, we get it from this equation, or the gradient of the graph that we plot before. So we can rearrange this equation because we already know that the heat temperature heat direction is from T1. T1 is normally will have higher temperature, and T2 is the lower temperature. So we rearrange this equation so we can eliminate the value of the minus sign here. So we'll get this equation. So the K value here is the thermoconductivity, which is a constant value, depend on the material, and it will be given in the table, or you can just Google it. You will find the value of thermoconductivity, depends on the materials. Conduction. Okay, so we look into the conduction definition, which is the transfer of energy from more energetic particles of certain to the adjacent less energetic ones as a result of interaction between the particles. So actually conduction also happen in gases and liquids, which is due to the collision and diffusion of molecule during their random motion. So because in the gases and liquid condition, the molecule is more scattered or randomly distributed. So the conduction happen due to the collision and diffusion. Okay, although it's randomly distributed, but it does not have any macroscopic velocity for these gases and liquid. So if the gases and liquid does not have any macroscopic velocity, so conduction will happen at the contact of these things, gases and liquid. Okay, so in the solid, it is due to the combination of vibration of molecules in the lattice and the energy transport by the free electron. Okay, so in the solid, it's due to the free electron. As we all know that the solid is closely bind, so it does not have any randomly distributed solid molecule. So it depends on the vibration from the temperature and also from the free electron in the materials. Okay. So this is the next is the rate of heat conduction through a plane layer is proportional to temperature difference across the layer and the heat transfer area, but it's inversely proportional to the thickness of the layer, which is the Fourier law of heat conduction. So these are the equation, okay, which is from the Fourier law. Okay, this is from the Fourier law. So we can rearrange this equation, or we can rewrite this equation in the terms of Q and Ka and dt and T and delta T. So you can just rewrite this equation, which I already derived in the previous slide. Okay, Fourier law of conduction already show you the Fourier law. the theory of it and how it derives the thermoconductivity, the equation, this equation. So now we goes into the definition of thermoconductivity, which is K, a measure of the ability of material to conduct heat, which is a constant value and depends on the materials, type of materials. Certain material has higher value of thermoconductivity, certain material has lower value of thermoconductivity. So and then we look into the temperature gradient, dt over dx, which is the slope of the temperature curve on the Tx diagram. Just basically the ratio of temperature difference over the distance. Okay. So heat is conducted in the direction of decreasing temperature. Okay, this is already mentioned also in the previous video, that the direction of heat always from the higher temperature one to the lower temperature one. And the temperature gradient become negative and the temperature decrease with increasing x. So the negative sign in the equation answer that heat transfer in the positive x direction is positive quantity. So it just mentioned here just to let you guys know that the heat transfer direction is from the high temperature side to the low temperature side. So the sign there is just to make sure that you are not how to say put the sign in the opposite direction. Just make sure if you know that the temperature difference, one side has high temperature and the other side have low temperature, so the direction of heat should be from the high temperature side to the low temperature side. Okay, so all this figure is the how to say the example of it. Okay, the rate of heat conduction through a solid is direct proportional to its thermoconductivity, which is the Fourier law of thermoconductivity. As you can see here, this side has 30 degrees Celsius and this side has 20 degrees Celsius, and Q here is 4010 watt per meter squared, which is the heat conduction. Okay, so for copper, the K is 401 watt per meter squared, and so that the if you look at here, so since copper has higher thermoconductivity, the Q value is higher compared to silicon, which has how to say almost 1/3 of the copper thermoconductivity value. So the value of thermoconductivity, the value of heat being transferred also lower. So with this fundamental idea, you can know that if you want to increase or want it to conduct heat higher, so we should use material that high thermoconductivity. But if you want it to be insulator, okay, heat insulator, so we should use low thermoconductivity materials. Okay. Okay, thermoconductivity. So now we look into the definition of it, which is the rate of heat transfer through a unit thickness of the material per unit area per unit temperature difference. So this is the thermoconductivity definition. As I mentioned in the previous slide, that it has constant value. Okay, this is the value of thermoconductivity. Okay, for some material listed in this table. Okay. So the thermoconductivity of material is a measure of the ability of the material to conduct heat. Okay, so I already mentioned here also, high value of thermoconductivity indicates that the material is a good heat conductor, and low value indicate that it's a poor conductor, poor heat conductor or insulator. So this is a simple experiment to see the thermoconductivity value in the materials. Okay, another terms that you need to know is thermodifusivity, which is from this equation here. Okay, alpha thermodifusivity is actually the ratio of heat conduction over heat storage. Okay, so the ability of the material to store and also the ability of the material to conduct. K is the conduct, which is to transfer the heat, and rho Cp here is the ability of the material to store the energy or store the heat energy. So if you look here, Cp here the specific heat capacity per unit mass, and rho Cpe heat capacity value. Rho here is the density, and time the Cp the specific heat, and alpha is basically just the ratio of heat conduction over the heat capacity, the heat storage of the materials. Okay. Okay, so it has explanation here. A material that has a high thermoconductivity or low heat capacity will obviously have a large thermal diffusivity. So we need to also look into the storage capacity and also the conduction ability of the materials. So the larger the thermal diffusivity, the faster the propagation of heat into the medium. Okay, so that's another thing. A small value of thermal diffusivity mean that heat is mostly absorbed by the material and small amount of heat is conducted further. So thermal diffusivity, because K value is at the top here, so it will how to say, higher value of alpha or the thermal diffusivity will show that it will easily transfer heat compared to the material that has low thermal diffusivity. Okay, so because K here is at the top over the storage of the energy, so it should follow K, because alpha is directly proportional to K. So if the value alpha higher, then K should be higher also. Okay, there's something like that. So this is this thermal diffusivity also a constant value. Okay, you can calculate based on the K and also rho and Cp. So basically it's a constant value, but in certain cases you need to calculate it manually lah. Okay, now we look into the second modes of heat transfer, which is the convection. Okay, the definition is the mode of energy transfer between a solid surface and the adjacent liquid or gas that is in motion and involve the combined effect of conduction and fluid motion. So conduction here happen at the adjacent of this solid surface. So because the value microscopic velocity is 0, so there will happen conduction. So it's in direct contact, so it does not have any movement, so it should be conduction. And then the rest is fluid motion. Okay, so this is the combined effect of it. So as I mentioned in the previous slide, the conduction also happen in the liquid and gases from the diffusion and also from collision of molecule. So without any microscopic velocity. So in this case convection, we have microscopic velocity. This is the microscopic velocity because they have air flow or we have movement of the air inside the room. Okay, so mentioned here also, the faster the fluid motion, the greater the convection heat transfer. Okay, we already know this because normally we'll put a fan just to make sure the air flow. Okay, for example, in our computer, okay, we have a cooling fan. That's why being called as a cooling fan, because the fan help in motion of the fluid, so it will increase the convection heat transfer. Okay, so in the absence of any bulk fluid motion, heat transfer between solid surface and adjacent fluid is by pure conduction. This is what I mentioned also in the conduction section. It is a pure conduction because it does not have any fluid movement. So if there is no fluid movement, then it will become a pure conduction. Okay, so let's see this example here. We have a figure here. So this is a stove. Sorry, not stove, it's a fireplace. And initially, we can assume that the air inside this room is stagnant, or it does not move. It does not have any microscopic velocity. And then this fireplace heating up one layer, okay, of outside layer of this stove. It heating up the air. So once the air temperature increase, it will decrease its density, so it become lighter compared to the rest or the other air because of the temperature difference. So the higher the value of the temperature, the lower the value of density. So because of that, the high temperature of the air goes up, and whenever it goes up, the air which at the top it goes down because of the uh, density difference. So it goes and move adjacent to this fireplace and also being heating up by this fireplace, and this process will be continuously happen until it reach the equilibrium state. Okay, so initially it is a conduction because the air does not move and does not have any microscopic velocity, but once the density of the air, okay, once the air has high temperature, it goes up. So once it goes up, and the cold air goes down. So this kind of thing now it become the convection heat transfer. So initially you start with conduction. After certain period of time, will change into convection, and this is being called as the natural convection. Okay, so it is a different thing for the forced convection. In the forced convection, we put a fan there so that the air movement is the air have a movement and it's in contact with the heat source. So that's another thing that's being called as a forced convection. And this thing I explained earlier is the natural convection. Okay, already explained a bit of it. We have forced convection and also natural convection. And so this is the explanation of it. Okay, forced convection, if the fluid is forced to flow over the surface by external means such as a pump, fan, or the wind. Okay, so naturally by wind also, if the air has the movement of air from the wind, or the air has microscopic velocity, we can assume it as the forced convection. For natural convection, if the fluid motion is caused by buoyancy force that are induced by density difference due to the variation of temperature in the fluid. This is what I explained in the previous slide for the fireplace and also the air in the room. So this is the example of forced convection here. Forced convection, and this is the natural convection. So for forced convection, we put a fan here and we force the air to move, okay, crossing or passing through the hot egg. So heat will be easily transferred to the flowing fluid and will increase the heat transfer rate of convection. For the natural case, because of the temperature difference, this hot egg will heating up the air adjacent to it, and once the temperature increase, the density will be decreased. So the decrease of the density will move the air upside, and the cold air at the upside will goes down. So this process happen continuously until the hot egg temperature start to equilibrate with the surrounding temperature. Okay, so these are the two explanation, the explanation of the forced convection and also natural convection. Okay, convection, it follows the Newton law of cooling, which is by this equation definition, it is proportional to the A and also the temperature of the surface of the fluid, of the solid body or any body that has high temperature minus the T infinity, which is the surrounding temperature. Okay, and H here is the convection coefficient. So A is the surface area. Okay, we can see here H is the convection heat transfer coefficient. Depends on the this value H depend on the condition, depends on the environment, and depend on the velocity. So in the next chapter, you will be you will need to know how to calculate the H value. We are interested in the H value in this convection heat transfer. AS is the surface through which convection heat transfer takes place. So the surface area of the body that has high temperature. Okay. TS is the surface temperature. T infinite is the temperature of the fluid sufficiently far from the sphere, which is the surrounding temperature. You can assume it to be something like this. Okay. So the convection heat transfer coefficient is not a property of the fluid. So this is what I mentioned earlier. We need to calculate the value of H to know which H value is suitable for the condition. Okay, it is an experimental determined parameter whose value depend on all the variable influencing convection. Okay, so these are the variable that influence the convection coefficient, which is the surface geometry, the nature of fluid motion, the property of the fluid, the bulk fluid velocity. So these are the parameter that being which will affect the value of H. Okay, so this is the typical value in the normal condition. Okay, you can see here, free convection of gases around 2 to 25 does not have any specific value. Okay, free convection of liquid around 10 to 1000. Okay, the range also quite large. Okay, forced convection of gases 25 to 250, forced convection of liquid 50 to 20,000. Okay, even larger the distance. Okay, the value of the convection. So how do we know which value should we use in our calculation? So we need to depend on the surface geometry, nature of fluid motion, property of the fluid, about fluid velocity. So from there, we can calculate the value of H depend on this condition. Thermal radiation, this is the third modes of heat transfer, and the last one. Okay, so the definition is the energy emitted by matter in the form of electromagnetic wave as a result of change in the electron configuration, molecular atoms. So the thermal radiation also does not have any intervening medium. Okay, for example, if you look at the conduction and conduction is within solid body, convection is between liquid or gases and solid. But for the case of thermal radiation, does not have any solid or any molecule also it can transfer the thermal energy. So thermal radiation is unique. It does not suffer from attenuation in vacuum. Okay, and one example is the energy of the sun reach the earth. That is the one example of the thermal radiation. Okay, so in the thermal radiation, we are interested in the radiation emitted by body because of their temperature. So in the thermal radiation also, um, all body emits energy. All body that has temperature above absolute zero emit thermal radiation. Okay, it's mentioned here. And it's a volumetric phenomena, but in our analysis, we usually consider it as a surface phenomena. Okay, so the thermal radiation follows the Stephen-Boltzmann law, which is given by this equation, where Q here, heat energy emitted by a body, this is the maximum value, is equivalent to sigma here, which is the Stephen-Boltzmann constant. AS is the surface area of the body, and TS power of 4 is the surface temperature of the body. So for the case of thermal radiation, you need to change the unit into Kelvin because it is the power of 4. So for other cases, conduction and also convection, you does not need to change the unit of the temperature. But for this case, you always need to change it into Kelvin, and also make sure that your Stephen-Boltzmann unit also in Kelvin. Okay, so you need to follow Stephen-Boltzmann constant units before you can uh, convert the temperature into Kelvin or degree Celsius. Okay, for this equation, which is emit maximum, it is some sort of black body, because the definition here, black body is the idealized surface that emits radiation at the maximum. So this calculation or this Stephen-Boltzmann equation calculate the energy that being released by a black body. For other cases of body which are not a black body, you need to times the emissivity here. Okay, so emissivity is the measure of how closely a surface approximates a black body for which emissivity is equal to 1 of the surface. And this is the range of value. If it's equal to 1, then it is a black body. Less than 1 is not a black body. Okay, so that's most of it. Okay, okay. Absorptivity here. This is the terminology that you need to also know in the thermal radiation. Okay, the definition is the diffraction of radiation energy incident on a surface that is absorbed by the surface. So the value also ranges from 0 to 1, which is the ratio of certain things. And black body absorbed the radiation incident on it. So for the case of black body, it absorbs all the energy that are being, how to say, radiate to the surface. Okay, so another law, which is the Kirchhoff law. Okay, we have Kirchhoff law here. So the Kirchhoff law state that the emissivity and the absorptivity of a surface at a given temperature and wavelength are equal. So this is what stated by the Kirchhoff law. So emissivity and the absorptivity of a surface at the given temperature, which is at the same temperature, should be same. Okay, so for example, something like this. Okay, this is one example. We have Q energy that being transferred from thermal radiation to a surface or a body. Okay, Actually when the body in contact with thermal radiation, a part of it is being absorbed. Here is the part that being absorbed, and a part of it is being reflected. Okay, so the Q absorbed here is equivalent to alpha, which is the absorptivity, times the incident, which is the total thermal energy that being transferred to this body. Okay, and the rest is being reflected. So 1 minus alpha, we want to calculate the reflected energy, it is equivalent to 1 minus alpha times the Q incident. Okay. Okay, another term that you need to know is the net radiation heat transfer, which is the difference between the rates of radiation emitted by the surface and the radiation absorbed by the surface. So basically, just as I mentioned in the previous slide, we have emissivity and also absorptivity. I also mentioned that in the previous slide, I also mentioned that any body or any surface that has temperature above absolute zero will emit thermal energy. So basically everything emit thermal energy, and everything also absorb thermal energy. So for this case, we want to know which is higher, being absorbed or being emitted. So, and this kind of thing can be calculated by this equation, which is Q radiation is equivalent to sigma, which is the emissivity, epsilon emissivity, sigma is the Savin-Boltzmann constant, and AS is the surface temperature. And this is the example of this figure bottom figure here. Okay, so Ts is the surface temperature of this body, which is given by this figure. Okay, and T4 here, T surrounding here is the surrounding temperature of it. So both of it emit and absorb, actually, as you can see here. So this is the energy from the surrounding, okay, incident on the surface, and this is also the energy from the air to the surface, and this surface also emit energy to the surrounding. So this is the energy emitted by the surface. This is also energy emitted by the surface. So this one is the incident, which is the energy from the air. So we can calculate the average or overall from absorbed energy and emitted by this equation. Okay, and this kind of phenomena depends on several parameters, which is the properties of the surface, orientation relative to each other, and the interaction of the medium between the surface with radiation, whether it's with the black body or not. Okay, so that is basically the net radiation of thermal radiation. Okay, so there is one thing that you also need to know. Okay, when radiation and convection occur simultaneously between a surface and a gas. Okay, this is one example where two modes of heat transfer happen at the same time. So, and for this case, we know that radiation can normally the heat transfer happen between two modes, which is the radiation and also convection. This is normal cases. Okay, so we can calculate this equation by using this value, which is Q total is equivalent to H, which is the combined heat transfer coefficient, times the surface area, and this is the surface area. Surface temperature. This is the surface area, and T infinite here is the surrounding temperature. So this is the case where the surrounding temperature can be considered as the surrounding. Okay, before this, we already looked into this equation and we does not consider the convection, but we have air in between the solid surface and the surrounding. So this air also contribute to the heat transfer, and this air is contributed by the convection heat transfer. So in this case, we have two modes of heat transfer, which is the convection and also radiation. So we can include here, it include both convection and radiation, and the equation is Q total is coming from convection plus the radiation equation. So this is the convection equation and this is the radiation equation. Okay, so H convection here is the convection coefficient, and here sigma is the emissivity, and epsilon is emissivity, and sigma here is the Stephen-Boltzmann constant. So as you can see here, we have the same temperature. Here is the surface temperature, here also the surface temperature, and here it become the surrounding temperature, the infinite temperature. here also the surrounding temperature. So we can rearrange this equation to be something like this equation. So Q total is equivalent to H combined, AS is the surface temperature, TS is the surface temperature, T infinite is the surrounding temperature. So we can how to say, take out this equation and we can expand it, because you can see here this is the power of 4 and this is only without any power lah. So we can calculate the H combined from H convection plus H radiation, and it's equivalent to convection coefficient of H plus sigma epsilon times the surrounding surface of the body plus surrounding temperature times in the bracket surface temperature power of 2 plus power of 2. So this is basically the H combined if you want to calculate it by using this equation. Okay, so I already explained to you guys the three modes of heat transfer. So let's summarize the three modes. Okay, modes of heat transfer. We have convection, convection here. As you can see here, we have three modes. The first mode is convection. Okay, the inside of this solid body is conduction, and without any medium is the radiation. Okay, we have circulation. So these are the three modes of heat transfer. Okay, first we look at the conduction, which is the transfer heat through a solid medium. Okay, in general, we can just summarize it as follow. Okay, convection is the surface of heat, the transfer of heat from the surface of solid body to a fluid. Okay, we have natural or free convection. The fluid is stationary, and after a certain period of time, because of the temperature difference, the density difference, buoyancy effect takes place, and it become the natural convection. Uh, and we have also forced convection, where we put additional equipment to support or to increase the flow. And the last is the radiation. It does not have any medium, intervening medium, can be transferred through vacuum. Okay, so the continuous emission of electromagnetic energy that occurs in all bodies, no medium required, can occur through a vacuum. Okay, now we look into the dimension and units. Okay, these are the modes of heat transfer. Conduction, first one is the conduction, convection, and also radiation. So conduction, the equation is Q conduction is equivalent to minus Ka dt over dx. So this minus sign can be how to say, removed if we change the position of temperature or the temperature difference. The higher temperature one minus the lower temperature one. K convection, Q convection is equivalent to HAS, which is H is the convection coefficient, A is the surface temperature, TS is the surface temperature, okay, of this wall, and T infinite is the surrounding temperature or the temperature of the how to say, surrounding. Okay, and last is the radiation. Surface Q radiation is equivalent to sigma, epsilon, sigma. Epsilon is the emissivity, sigma is the Stephen-Boltzmann constant, AS is the surface temperature, and T as power of 4 is the surface temperature of this black body, minus for this case it is not a black body, because it has epsilon value. If it is a black body, then the epsilon value will be equivalent to 1. Okay, minus the surrounding temperature, and here is the surrounding temperature with the power of 4. So the heat transfer value, Q value here is the heat transfer, joule per second or watt. This one should be capital Q. Okay, K is the thermal conductivity here. This one is thermal conductivity. So the unit is watt per meter dot degree Celsius or watt per meter dot Kelvin. And then the surface area, all of it is the surface area. This is the cross-sectional area. This is directly the surface area that in contact with the fluid which are flowing, and this is the surface temperature which are in direct exposed to the surrounding. Okay, so T here is the temperature, can be degree Celsius or Kelvin. Okay, for the case of radiation, you need to make sure the Stephen-Boltzmann unit, whether it's in Kelvin. Okay, this is the Kelvin or degree Celsius. Okay, X is the thickness. Here is the thickness. H is the heat transfer coefficient. This is the heat transfer coefficient. And the unit is watt per meter squared dot degree Celsius or watt per meter squared dot Kelvin. Depends on the temperature. Okay. But for the case of conduction and convection, because it is just a temperature difference, normal temperature difference, you can use regardless Kelvin or degree Celsius, because um, degree and Kelvin has the same unit, same temperature difference value. Okay. But for radiation, because the surface temperature is with the power of 4, okay, so we need to change it into Kelvin. So the last is the Stephen-Boltzmann constant here. The unit is watt per meter squared dot Kelvin with the power of 4. So you need to make sure that this value is in Kelvin. If it is in degree Celsius, then you need to change the surface temperature of the radiation equation and surrounding temperature into degree Celsius. Okay, these are the example of example question for these three modes of heat transfer. Okay, I need you guys to do it so it can be considered as your attendance.